doing this monumental organization of so many speakers, which looks like a almost impossible task, but yeah, so they have managed to pull it up. So I'll be talking about dynamical freezing and its immunity to thermalization because of suppression of resonances. So first so there are many people who contributed to these works for years, so it will be not working. Okay, you haven't put it on or something? It's on, right? Yeah. Check it. Hello? Hello? Is it working? It doesn't seem like, or is it?
It's okay.
Too close? No, it's pretty.
Yeah, I think
It's
noise
pretty.
is there, but we can hear you.
So fine in the sense that it's not working. Okay. So whatever it is. So yeah. So many people contributed, but oh, what happened to this?
Is it your laptop?
Yes. But it just worked a while
Yeah,
back.
some loose connection. That one is used probably. Just check. No.
I cannot do that. Okay, this is new. Okay. Okay, so the main thing of the interacting version of this phenomena was developed by one of my student, Ushmi, and Anirban and Shagnik. They might be here in the audience. They have contributed a lot in the later stage of the development, and then there are many other people who joined. So I'll just give you a very basic idea of this thing first, and then we'll go to the technical part, which is particular to this talk, which is the resonances, which are the resonances. But before that, I would like to give a general idea because most of the people do not know what it is. So the idea is if you just shake something, you expect that since you are providing energy to the system repeatedly and continuously, it will just absorb the energy and the things will become more chaotic. So if you just put a drop of some paint or some color in a bulk of water, it will just dissolve and eventually dissolve and go everywhere with a lot of probabilities. So this will be entropically maximal state where everything is uniform. And what happens if you shake it? Obviously, our normal experience said it will just happen faster. So the main idea of this dynamical freezing was that it turns out that it's not always the case in the quantum mechanical situation. So what happens is just in a very schematic overview of the system. You take some interacting spins, you drive them periodically in a unitary manner. So you have a Hamiltonian which is a periodic function of time, and if the drive is strong enough, then at some limit there emerges certain quants of quantities which are not present in the initial undriven system. So you take a lot of interacting particles, they are interacting with them, they are perfectly bona fide ETH abiding ensemble, and you shake them very strongly, and then out of the shaking there appears some new conservation laws which stops them from thermalizing. So if you have this particular operator, some operator which is defined on each site where the spin sits, and you take a sum of them, and then this can be an emergent conserved operator. We call it ECO. And in terms of this operator, these are the various degenerate eigen subspace of this operator, and the drive basically breaks it into dynamically disjoint sectors, where each of these subspaces into dynamically disjoint sector, which means the subspaces where the eigenvalues are same, they can mix, but with different eigenvalues they do not mix. So the Hilbert space does get fragmented, and so it gives a very kind of interesting and rich phenomenology in terms of recent constructs. So there is a fragmentation of Hilbert space. If you start with a fragment where there is only one or a few members of this particular eigenvectors of this operator, then you get they do not mix with all others, so they look like a many body scar.
So you have ordered L fragment, right?
It's an ordered L fragment, depending on how many conservation laws you have.
No. For
Yeah.
everyone,
Yeah. Typically, if you don't have disorders, if you have disorders, you can have exponentially many. So the general structure.
That statement is true for any kind of drive.
Drive.
You have not given detail.
I'll come to the specifics here. So the general structure is you have a drive. The drive term has to be classical in the sense it's function of only one kind of Pauli matrix, for example, but classical in the sense it should have a lot of degeneracies and polynomial in number of eigenvalues. In that case, it will have a large degeneracies, but their gap through the spectrum will be finite. For example, a transitionary invariant operator with just only one kind of operators which commutes with themselves. And then the Hamiltonian will have a part which commutes with the drive, of course. There can be part which commutes with the drive. And then obviously there has to be a part that does not commute with the drive. So that's the structure basically. And there is a drive amplitude which we'll call large or small, and then there is a periodic function of time which constitutes a drive. So now this part which commutes with the drive, that can be a sum over, for example, in case of Ising spinning case, it can be a sum over many kinds of correlators which are all in X. So for example, in this case you can just have two body correlators where Kr is the strength of the correlator and Crx is the correlator itself divided by 1 by L. So that's an intensive operator, and C0x is just a field, and your Hamiltonian is just L into C0 is a drive term in this case, in this particular case, and each of these term in this Hamiltonian they will turn out to be an independent conservation law. This is very weird because you would expect that a part of the Hamiltonian itself as a whole will be conserved, but it turns out, I will just take a little bit of water. I have developed diabetes, so I get dry mouth. Okay, so each of these terms will serve as a independent conservation law, and as Krishnendra was asking, saying that still for each of them the number of fragments will be polynomial in L, but together with them they can be very complicated structures. So first instant was shown in this simple transverse Ising model. So you have a transverse Ising system and you are driving the transverse field with large terms, large field, and then instead of going to a infinite zero temperature scenario, which people expected at that time, because even in two level, so this is an integrable model, but even in the integrable model, the Hamiltonian doesn't commute with itself at various times. So people thought, why wouldn't it absorb energy? Because integrability is in terms of things which commutes with the Hamiltonian. The Hamiltonian does not commute with itself at various times, so it should basically nothing will commute with the Hamiltonian, so it will absorb energy. And if you go to the momentum space, there are two-level systems, but these two-level systems can also heat up to infinite temperature, because you can have equal distribution of population there. But it doesn't happen so. It gets to certain very special states depending on your frequency and amplitude, starting from a particular initial state. And depending on your drive amplitude and frequency ratio, they go to this kind of a peak valley structure, where the peak means you are very, very close to your initial value. The valley means the values deviates from the initial value a little bit, and then there are peak valley like structures. For this integrable model, this can be worked out exactly, and you can calculate these structures. These green lines are numerics, and the black lines are approximate analytics. This comes out to be this kind of a Bessel function of this combination of amplitude and frequency. So it turns out,
So at very high frequency, it goes towards zero, is it?
at very high frequency, it goes towards zero. Why? Why this is so? Because then at very high frequency, you can just drop this term. So we are started with a term which is aligned in x, and you are left with only zz term. So the x thing is completely corrupted. So
Going towards zero is like spreading more, is it? Or,
yes, but you start. Freezing is in this x direction.
this one goes to half, this one the point. This one goes to half.
This one goes to half. This guy goes to, sorry, so this magnetization expectation goes to 0, because population goes to half.
From here, if I just take average mx to be 1 by 1 plus that, the Bessel function goes to 1, no?
Bessel function,
When omega tends
Yeah,
to infinity.
yes, Bessel function goes to 1. Then it's
So
1 by
it
2.
will go to half, no?
Yeah.
So you're talking about the large omega part.
yeah.
Yeah.
Omega is going to infinity.
Yeah.
so
And
Yeah,
G
no,
of
but
zero is
no,
plus one.
but this is an approximation. There are other terms which actually kills it. This is the rotating wave approximation. So this term will go to half, but there will be other terms which will eventually go to drag to 0.
So is the approximation which order? What is the approximation?
The approximation is called rotating wave approximation. The order is very difficult to say, because you do not expand in the power series. What you do is you just have e to the power I into some terms.
Is that going to be better at larger omega?
Approximation is going to be better at larger omega. Yeah,
That should be.
yeah.
It's surprising that at high frequency this does not reproduce the large omega.
Yeah. This omega going to 0, omega going to infinite limit, and other limits, there are non-commutativity of these limits. After all, it's a divergent series, so you do not know what exactly happens.
So is this integral in the sense that quasi-energies follow some Poissonian distribution?
Yes, it's in standard. It's you can map it to free fermions, basically. So anyway, for square pulse, actually, you can show this phenomenology exactly. So for non-integrable system, we had integrability breaking next nearest neighbor term, nearest neighbor interactions, and a field. The longitudinal fields also break the integrability, and then you have a drive in the longitudinal direction, and of course a transverse field, so that they really have a dynamics. So in this setting, following our previous prescription, which actually came out from this setting, there are 3 conservation laws, because H0 has 3 parts. One is magnetization, another is the nearest neighbor correlation, and the next nearest neighbor correlation. So if you see this, how well they are preserved, this is the magnetization. You can see this after a certain drive amplitude, this is actually frozen. And if you start even with a hard random state, you can do the autocorrelation calculations. So this is 10 to the power 11 cycles, and these are the three quantities which are supposed to be conserved, and you can see this conservation level is this. And if you zoom in, then up to 4 decimal places, this is the conservation level. So the thing is, the conservation laws are approximate because there are fluctuations, but they are perpetual. Why they are perpetual? Because 10 to the power 11 is not infinite, but if you just draw the diagonal ensemble average, they will fall somewhere here. I just didn't draw it here. So the thing that happens is these quantities which you look at here in the H0x, they do not commute with this guy, and their coefficients are not very large. So each of these terms have a very large non-commutator with the Hz term, which flips them. But nonetheless, these things are conserved at this level. Okay, sorry, I did something wrong. Okay. So the question is how strong the field should be. So a scan with respect to the drive amplitude shows that there is actually a very sharp threshold of that, above which the system freezes. And here is this is the dynamics of diagonal ensemble, the dynamics starting from a particular initial state all up, and we are plotting the diagonal ensemble average, which is the infinite time limit of the dynamics. And if you plot the threshold in the log, you will see that the threshold becomes sharper and sharper, but doesn't move with the system size. And a much better view of this can be done if you do a spectrum average. So you take all individual x eigenstates and do the dynamics, or take the diagonal ensemble average and subtract the value of the particular eigenstate of this eigenvalue of this operator, and this difference going to 0 means they are very well conserved. So beyond a particular value of the field, you see that things are almost 0, and there is a system size independence, system size flipping. So after a particular value of the field, actually the larger system, the errors are smaller, so they are more frozen. So you might think that this is happening because we are working with small systems which still has discrete spectrum. So we started observe this thing also with infinite systems using TEBD. This was some project, this one done by all these people, and I was also somehow involved. So there it turns out that if you go to very large system sizes, which you can surprisingly go for this particular in this particular regime, because your entanglement doesn't grow, and you allow the system to evolve as much as it can. That means you don't put any ceiling on the entanglement by hand. You still can simulate the system up to very, very long times, 10 to the power 5 cycles, and you see that there is a regime where the entanglement growths are so severe that you cannot actually simulate the system beyond this point. But after that, you can simulate even an infinite system pretty stably here, and the threshold point is pretty close to what we got from the exact diagonalization of the small system. So somehow, when you even have a continuous spectrum, still this freezing works. So it's not because you are creating large gaps which are protecting them. So if you scan in terms of omega, then you will see some peak valley structures, as you saw in the integrable case. At the peak points, the things are absolutely strongly frozen. I mean, very strongly frozen, not absolutely in the sense that it's not exactly conserved. It has fluctuations, but fluctuations are minimal. And these are two results for zero temperature and very high temperature initial state. So it's a density matrix we did the dynamics with, and it turns out the quantities which are the magnetization divided by its initial value, which can be very, very low because we have taken a thermal density matrix, still shows this kind of peak value behavior, and 1 again still means it's very, very close to its very tiny initial value. And these peaks occurs in the square pulse case as hdx equal to some integer multiple of omega. So interestingly, this came out in a recent experiment in Nature, where they picked up our term dynamical freezing, and they used this phenomena to contest with decoherence for doing quantum magnetometry. In general, they were doing the setup for quantum metrology, and they found out that doing this particular trick, this dynamical freezing, where you are actually freezing a many body Hamiltonian rather than doing a single spin scheme, which is very far used nowadays, which is called dynamical decoupling. It keeps the state stable by an order of magnitude longer time, and then you see the same peak value structure we just showed. They have done it experimentally, and they have also borrowed this cartoon from Ushmi's paper, which is actually done by her. So they can apply these things still in certain quantum technological applications. Nonetheless, this is a tremendous mystery we do not understand, because we do not understand why there are these conservation laws. First of all, we have no idea or concept which says a part of the Hamiltonian, effective Hamiltonian, will be conserved. When a Hamiltonian is conserved, you think the whole part of it as an energy, and then you have ideas. But in this case, each part of the correlations are conserved. And to see how stable they are, sometimes you might think that, okay, finite sizes are finite sizes. Infinite sizes at finite times are still finite times. So we want to set our clock by using internal timescales, the hierarchy of timescales. So what we did is, we know that if you have a perturbation series, the first order processes are the fastest processes, because they have a small parameter to the power 1, and the second order processes are epsilon square, so they will be slower. So L spin processes are extremely rare. It takes e to the power L order process time scale. So we use this hierarchy of time scale to check whether these things are really, really stable.
You have 10 minutes in.
Okay, wonderful. Well, so I have 1 minute extra for.
I said 10 minutes plus question.
Plus question.
Including question answer.
Okay.
10 minutes total.
Okay, don't worry. So, this we take this null state, and if you have all these three conservation laws acting, if you believe these things are still conserved, though we do not know why they are conserved, but suppose we believe they are conserved, then you will see that you cannot go anywhere from starting from this null state to the other null state. The other null state needs L number of spins to flip. So this takes an exponentially long time, which is very well known, because it's a tunneling which crosses a barrier of width L and also height L actually. So what we are trying to observe is what happens in this time scale. This is purely an e to the power L time scale, and the hierarchy of flipping spin, this is the largest one, because 1 spin flip, 2 spin flip processes has to be slower than L spin flip process. So we start with one null state. This is the blue one. It's overlap with the wave function of this null state, and the yellow one is overlap with the wave function, time dependent wave function, with the other null state, and L is the sum of their total weight. So we see it starts from one null state, and then it goes to a superposition of both of them, which is a GHZ state, and then it switches over to the other null state. Probability goes down, and then it starts oscillating with an exponentially large period, which is 10 to the power 7 for L equal to 8. But nonetheless, any single spin, two spin flip or three spin processes which could occur because your spin flip term in the Hamiltonian is actually a single spin flip term. It's just a transverse field which just flip one spin. None of the one spin, two spin, three spin processes are occurring. So it directly goes from one null state to the other null state without flipping all the one spin flip, two spin flip processes, which are local processes and hence have a very shorter time scale, much shorter time scales. So that means that even if you increase L, this time scale grows proportional to the L as you expect. So it's for L8 it's 10 to the power 7, for L12 it's 10 to the power 9. So everything is in terms of the nail to nail tunneling, everything is in order, but still one spin flip, two spin flip, three spin flip processes are not happening because they are violating these conservation laws. So now the question is why these conservation laws are so strongly respected in spite of the fact that your spin flip operator in the Hamiltonian is a single spin flip operator. Okay, now we come to the actual technical part of this talk, which are resonances. So these are particularly interesting for the people who worry about resonances like Shomu, Arthi, and all other people doing MBL, etc. So, and many others, of course. So there are resonances. So if you stay at a freezing peak where everything is supposed to be close to 1, like your autocorrelation function, for example, and you change some of the parameters of the Hamiltonian, like the static, this is H0x is a static coefficient of the static field in the Hamiltonian. You see at certain points the freezing goes away and it gives way to thermalization. Certain discrete points. So we can do a theory. We did it here in this particular paper. Actually, Diptiman came up with a very nice theory. And later in this paper, we have a more general theory. So he came up with the first order resonance theory.
Earlier you said Hx should be n times omega to see the freezing, but now for Hx equal
No, it's
omega,
Hx0. It's the static part of the Hamiltonian. Well, that was Hxd. It's a drive amplitude. We just want to move some parameter, maybe kappa, maybe j, that's fine, anything. So then you can calculate where these resonances will be from Dyson series basically. So there are these black lines where we expect the first order resonances. Then there is this faint yellow lines. Why these are faint, you have to ask Shagnik because he plotted it. And these blue lines are the third order resonances. So if you keep on drawing these resonances, fourth order, fifth order, this will completely become filled up with these lines and your ceiling will just come down. But very interestingly, you just see numerically just the first order resonances which are very deep going down way down going down all the way, and then there is this second order resonances. This comes down a little bit but not all the way, and there is nothing at the third order line and there is nothing beyond that. I forgot to mention Shumilon because he was interested in resonance guys. So anyway. So it turns out that the second order resonance still goes down with system size, but there is no appearance of the third or higher order resonances. We do not see them. So one way of thinking how thermalization happens is proliferation of resonances. You have states which are conducive of these transitions, so you go from that state to that state, the other state with absorbing a photon, which comes from the drive, and then you go on that way and eventually heat up. That is the idea of Floquet heating. But here you see that first and second order resonances are of course discrete lines, so there are ample space between these resonant lines, first and second order, where you can have a continuous stretch of parameters where there is no resonances. So nothing heats up there because of the resonances. So it remained a mystery to us and still a mystery to some extent, but we managed to resolve some of it. So for that you have to look into this Dyson series expansion, and if you just massage the nth order, you get a condition for the nth order resonance, any nth order. And you look at it, you see this width of this resonance goes as 1 by drive amplitude. So at each level. So the third order resonance, so for each of the each level of this resonance, it's 1 by hdx to the power n. So if you take the series of all the resonances within a given parameter span, for example, let me explain it, it's a bit tricky. Suppose you take this much parameter span, and you count all possible resonances of all orders appearing there, how much space it takes within this stretch of parameters? That's the question we were asking. And it turns out that you can estimate it from this Dyson series. And in very general situation, if you sum all the terms up to infinity, you can do the sum. It turns out to be 1 by the amplitude. That means if you increase the amplitude, the total width of the parameter space covered by the resonances of all order from first to infinity is finite, and not only finite, you can make it thinner and thinner as you wish by increasing the drive amplitude. And then what happens is this. So first order resonance is, suppose you start with a state, it has a first order resonance here. Generally first order resonance, when there is a first order resonance at that point, there are second, third and fourth order resonance and higher order resonances. So it just goes from first order resonances, then it goes to the second order resonances. This is the axis of your parameter. And then at the same parameter value, you have a third order resonance, and so on and so forth, and you have a percolation in the Hilbert space. But if you go to the second order resonances, then this is, so by the way, this is a width we estimate. This is a width we actually get numerically, and this red spot are the points where we expect the resonances from the time dependent perturbation theory, which is the Dyson series. However, the resonance actually shifts a little bit and shifts randomly. That's very important. And that's why what happens is, in the second order case, suppose you have a resonance here, the position where the resonance actually appears and the position actually where you expect the TDPT resonance have a very thin overlap. This is this thin faint shade here. And the third order resonance, from third order on, depending on the parameter we set, they are completely separated. So that means, suppose you have a resonance and you expect, okay, this is a second order resonance, but we we are not supposed to have a third order resonance here, but close by there can be a third order resonance, there can be a fourth order resonance, there can be a nth order resonance, which are very, very close, but they will miss this line because they are also very, very thin. They are getting exponentially thinner. So basically the density of resonance around this point remains actually almost zero. And that's why the percolation breaks. So basically there is controlling this 1 by hdx, you can basically control the percolation threshold. So the total width of a parameter regime covered by the resonances is somewhat your P of the percolation. So we have a theory which I am not showing here. So this is the conclusion. So you don't have resonant percolation in the Hilbert space in a dynamically frozen system, and so only thing which is left is non-resonant heating. What happens with that is still a mystery, and why there are conservation laws of this form is a mystery. Anyway, thank you very much. This is our institute. We are all welcome to visit anytime. Write to us or Krishnendu or on.
Thanks, Arnav, for